Okay, there we go. All right. So this is Cameron, Matt, and Austin, and we did our final project on just the Nintendo 64 OS. So just about the hardware real fast, the RCP, the Reality Core Processor, is the center of the game system, and so all data passes through it, and it acts as the memory controller for the CPU. And the RCP runs the graphics and the audio microcode, and the display portion of the RCP renders into graphics frame buffer located in main memory. And so the CPU and the RCP work at the same time, and so threads are executed on the CPU, whereas tasks such as microcode are run on the RCP. And so they're always running in parallel, so it helps speed up the process so they're not waiting on each other. Alright, so about the CPU. It's a R4300, and it consists of an execution unit with 64-bit registers. It's got a 16 kilobit cache and 18 kilobytes of write-back cache. And it's a 32 entry TLB for virtual to physical address calculation. And the Nintendo 64 game runs in kernel mode with the 32-bit addressing. 64-bit is available, but a lot of the C calling conversions is worked best with 32-bit, and so here are some of the calls that it can make for the different registers. Alright, so in runtime, it's non-preemptive execution, so whichever thread is running will continue to run until it either stops or it gets a message from another thread saying that it needs to run. And so it's usually whichever thread has the highest priority, which is priority scheduling. So whichever thread has the highest priority will run. And so if a thread is running and a new thread is created that has a higher priority, that currently running thread will stop running and the higher priority thread will run until it is done. And the threads communicate with each other through messaging. And so another way that a thread can be stopped is interrupt messages, which it tells the thread to stop running so that way it can run. So when the CPU writes data, the cache may satisfy it, just like you would think it would, and the CPU writes data. The data is written to cache first, and then later on is flushed to main memory. So it kind of like does all of its writes at one time to save from always constantly writing back and forth. And there's no default dynamic memory allocation. It's all static, but the game applications themselves can implement their own form of dynamic memory allocation. Just the game has to take care of that, and the OS itself does not take care of that. The schedule thread is responsible for collecting display command lists from other threads and assigning them to the RCP tasks list. So that's the different bits of microcode that it needs to execute. Okay, so now about threads. Each thread has its own stack, and the operating system is a collection of routines that can be called in a thread. The operating system controls which threads is running on the CPU, and threads can access all parts of the physical memory of the OS. The game program creates a task list and calls an OS routine to load the appropriate macro code into the task list that the RCP then executes. Priority. And so the different thread states that we have running, which is currently running, runnable, so it's in the queue to be ran, stopped, which are newly created threads that have not been fully processed and put into runnable yet, and then waiting is when either an event has occurred that stops a thread or a higher priority thread has come in to make it wait until its turn. And here are the different commands or calls to make threads. So we have create thread, destroy thread, we have yielding it, start, stop, and then getting the thread ID and setting the thread primitive, I think that's called, is just ways that the OS can discern which thread does what. Okay, so different exceptions or interrupts that the OS can handle. The CPU supports 8 different interrupts, and so if the CPU runs into an interrupt, it will look on the chart. If it is not on the chart, then that thread is just destroyed and then recreated, because the CPU doesn't know how to handle any exceptions that aren't on its chart. And then for events, if the interrupt is on the chart, it then goes to the RCP, which then handles it in the event chart, and then it looks on the event chart to see what to do. And again, if it's not on the event chart, then we'll just destroy the thread and recreate the thread to make it as simple as possible. Alright, so I/O functionality. The I/O subsystem is mainly designed for optimal throughput and response, and not for portability and generality. And so there's a lot of asynchronous I/O, which is the preferred choice for real-time game environment. So whenever it receives something from the game, it will just automatically shoot it out instead of waiting for like the entire package that it's asking for to be sent out. So in the system, mutual exclusion is not implemented as a general scheme for all devices, but rather as a specific scheme for each identified shared device. So whenever it's talking to the audio or like the video, it can only be doing a single I/O at a time, just that way it's not like receiving input and sending output at the exact same time. And some of the systems that keep track of this, we have the system exception handler, which keeps track of all the exceptions and interrupts that happen on the machine. The device manager, which keeps track of all the DMA requests to and from all the different devices. And the device dependent system interface, which has 2 layers, high level abstraction and a low level. And so this keeps track of the single processor functions, display processor functions, video interface functions, audio functions, peripheral interface functions, and the controller functions. Alright. So memory management. The CPU address translation takes place in either 2 ways, the direct mapping or through the translation look-aside buffer. And so the N64 includes DMA engines that access DRAM directly. And these DMA operations are initiated by the CPU, and the DRAM addresses passed to the interface routines are CPU virtual addresses. And the data cache implements a write-back replacement policy. That means that data stores are held in cache until the entire cache line is written back. And this usually is due to a cache miss that requires the same cache line. Alright, so prior to loading a segment into memory, the application must invalidate the corresponding cache lines, just so that way it's not loading in previous cache data into memory. And the Nintendo 64 hardware contains 4 megabytes of 9-bit DRAMs, and the normally hidden 9th bit is used for anti-aliasing and Z-buffering hardware. It is recommended that the frame buffer and Z-buffer reside on different megabyte banks to take advantage of caching in the DRAM circuitry. Oh, this is mine. So about the translation look-aside buffer, there are 32 entries, each of which maps to 2 physical pages. And each entry is independent of each other, so we have an index number that implies nothing about the mapping, and the entry can hold any type of mapping. And so the different types of mapping that are supported, we have 4 kilobytes, 16, 64, 256, 1 megabyte, and 16 megabytes. And and so so 2 TLB entries cannot be mapped to the same virtual address. And so if this happens, the access of the address will cause the TLB refill exception, which will just basically delete everything in that TLB and then reset it.
All right, so moving on a little bit about the graphics programming. Me and Matt are both gonna split up a little bit. There's two different types of graphics processing. So the RSP is a CPU-like unit that acts as a single interface between the application and the graphics pipeline. So like kind of just like the one thing that like will translate stuff for it. So programs that run on this RSP are called tasks, which Austin talked about earlier, which are a series of OS calls stored on a task list. The RSP interacts with the display list, sending it the data for each individual frame that needs to be displayed. So that's each command gets sent to that display list, which will then work through to be displayed. So the geometry engine in the RSP implements a fixed point matrix engine, which is just a 10 deep modeling matrix stack, which new matrices to be displayed on the display list will be pushed to it and can be popped off the stack. But most of the time, when you push a new matrix to an existing on the existing matrix stack, it will multiply it with the top existing item on there, just to make sure all the display is looking like what it should with each other. So the RSP also includes a vertex buffer, which contains up to 16 vertices. The RSP works with the command GSSP texture, which set the current texture state of each of the matrices. It is important to note in RSP, clipping is always enabled, which is just like making the display more clean when you're viewing the game. However, clip ratio and near clipping can be used by the developer themselves to make it even cleaner. Vertex lighting and vertex fog state are important functions because, as you can imagine, like those set with like lighting on different like sceneries, or you can make fog appear on different sceneries. Since the RDP is a physical address machine, which Matt will talk about next, the RSP must translate its segmented address for the display list into physical addresses so that then the RDP can properly display everything.
So while the RSP works quite a bit with more 3D modeling as a whole and displaying, the RDP takes it down all the way to the actual rectangles and triangles and rasterizes those and produces high quality pixels that are textured, anti-aliased, and Z-buffered. So there are 6 major logical RDP pipeline blocks. First, the rastersizer, which will generate the actual pixels that will fill all the triangles and rectangles, and the texturizing unit, which will take in values for a pixel and fetches the onboard texture memory for the 4 nearest texels to the screen pixel. The texture filter, which takes the 4 textiles generated by the texturizing unit and produces a simple bilinear filtered textile. So it just kind of combines those 4 into that one textile. Then the color combiner is just kind of a paint mixer essentially. It combines the textiles from the TX and the stepped RGBA pixel values from the rastersizer, and it can mix the colors using a linear interpolator. Then you have the blender, which takes the combined pixels and blends them against the frame buffer pixels. And also plays a major role in the anti-aliasing steps, which we'll take a look at later. The memory interface, which finally is the last step, which provides a simple interface to the frame buffer memory, which, like Austin said, the Nintendo 64 uses 9-bit DRAMs instead of the regular 8-bit DRAMs to gain 2 extra bits per color or Z pixel to get a little bit more detail in those. So looking at the textures themselves, over here you can see the block diagram that kind of goes through the flow of everything to finally pop out a textile color. So the RDP contains an on-chip texture memory called the TMEM, which buffers all of the source image information used for the texturing. Since texture requires a large amount of random access with constant time to access texture memory, it doesn't make sense to texture directly using the DRAM, but the TMEM is 4 kilobytes and can have up to 8 tiles, a tile being a section of an image. So in this setup, the TMEM should be considered processor cache, essentially from the point of view of a programmer. Each tile is loaded into the TMEM using the commands called load tile, load block, or load tlet. If the image is too large, the tiles must be divided based on their texture coordinate values. So, whichever is closest to each other, they'll just kind of start at the top and work their way through the full image. Now, a little bit about anti-aliasing. The N64 had horrible resource costs and memory requirements, so a new technique for anti-aliasing was developed. First, this method relies on the fact that different objects have different anti-aliasing requirements, so different render modes are configured for each object. So you don't need heavy anti-aliasing on something that's really far away. Next, there's display order restrictions for different types of objects, such as displaying a transparent object after all the opaque ones. And then lastly, the anti-aliasing of silhouettes were able to be done in a post-process during the video output as seen in the data flow chart. So as you can take a look at the data flow chart here, you can see all of those pixel colors, pixel coverage, and memory color. It all goes into part of the blender, as we saw up top a little bit earlier. And that is then processed further, and also anti-aliasing the silhouettes is done while it's going out in the video interface. You've actually can see this in a different product out there right now in the HDMI cable that does additional anti-aliasing. It's very interesting. Audio library and tools. The N64 audio library consists of 4 software objects: the sound player, which is useful for the playback of single sound effects or streamed audio and is capable of playing the ADPCM compressed sounds or uncompressed 16-bit sound. Sequence player exists of either 2 parts. The first type plays back type O MIDI sequence file, and the second type plays back a format of compressed MIDI unique to the Nintendo 64. In both types, the sequence player oversees sequence, instrument bank, synthesizer, resource allocation, sequence interpretation, and MIDI message scheduling. You just have to work with your composer as to which type you want to go with. The synthesis driver, which is responsible for creating audio command lists, which are then put into task by the application program and pushed to the audio synthesis microcode. And then the final part there is that microcode as process the tasks passed to it by the application and synthesizes stereo 16-bit samples, which then go to the audio DACs. As for audio tools, the Nintendo 64 has an instrument compiler, which is used to prepare banks of sounds and control information that gets handled to the sequence player and the sound player. Also has sound compressor and decompressor for the ADPCM format and MIDI file converter and printer. And the tool instrument editor provides 3 primary users. As an editor, it allows real-time editing and playback of the instrument banks and effects. As a player, it allows for external MIDI devices to play back MIDI on the Nintendo 64 hardware. And as a profile, it profiles and measures audio resources that are being used during playback. Fascinatingly, all multi-byte data types are stored with the highest byte first, or as a big endian system, which is actually opposite of most Intel systems. Is what I found here in the auto section. Usually the bank files store the audio and control info needed to create sequencer MIDI events. On the Nintendo 64 specifically, this info is encapsulated in two files, the bank file and wavetable file. The bank file has information such as the program number to instrument assignment, key mapping, tuning, and envelope descriptions. It gets loaded into DRAM during playback. The wavetable file, however, has the ADPCM compressed audio data. Because the sheer size of this data, it is streamed into DRAM and then into the RCP only when it is needed. The formats for these files are optimized for the N64 to be used with the sequence player and sound player. They contain no textual information or data not directly related to playing back audio. Many features usually found in standard patch and wavetable formats like AIFF files were cut in favor of smaller files in ROM. And so all this together, when a game starts up, it creates and initializes a sound player and sequence player. It then loads sounds effects into the sound player and loads a bank of instruments and MIDI sequences into the sequence player. So to play a sound effect, the game tells the sound player what the target sound will be and then when to play it. For a MIDI sequence, the game must first load the sequence, attach that sequence to the player, and then say when to start playing. So there are two main sections for the audio system software. One part runs on the CPU and the other part on the RSP. The audio must share the RSP with the graphics processing. The RSP is where most of the low-level processing is, and this is also where the samples are mixed into an output stream, where it is then fed into a pair of DACs for stereo output. The reason banks are stored into two files is so that the raw audio data doesn't need to be loaded into RAM, only the data pointing to the samples and the value for the playback variables. So every time a sound is played, a very small portion of the sample is loaded into RAM buffer. After playback, it's immediately discarded and the buffer is reused for another portion. It could be the same sample or a different one. And with this system, a relatively small amount of RAM is needed for the audio.
All right, so moving more on to the usage in the memory and how to utilize all the memory usage the best. So the amount of RD RAM needed by the audio systems depend on many factors, such as how many sounds are playing at a given time will usually have a large effect on the buffer. And most of these buffers were made to be large enough to handle the worst case scenario. But most of the time, they usually only uses, instead of the 4 buffers, only uses about 2 of them. So although these are where memory can be best optimized, there are buffers which are important but have a less high need to be optimized. Those include the audio thread stack size, synthesizer update buffers, and audio heap. It is important to note that when you're working on this, even though graphics can be rendering at 30 frames per second, because we weren't really up to 60 frames per second by this time, it is still appropriate for the audio to be rendering at speeds a lot faster, because you can have background music playing faster than the video's rendering. When optimizing audio memory, the most important thing that we will go into deal with later is optimizing the buffer usage. As I mentioned earlier, only using stuff that needs to be used. In the worst case scenario, the audio OS will need 4 of these buffers, but like I said, it only usually uses about 2 of them. To make sure we aren't wasting memory space, the system will free up any buffers that haven't been used in the few frames, thus optimizing the usage of these buffers. So the audio and graphics towards the Nintendo 64, as both Austin and Matt mentioned, are shared by the CPU and the RCP. The work that needs to be done is stored on the command list I talked about earlier with the RDP stuff. So the CPU is responsible for the generation and management of the command list. It is first responsible for generating all the commands, and that turns the task into commands that the RCP will understand, which is the microcode that Matt talked about. The RCP is responsible for processing these microcodes. So the video frame can usually just be updated at a constant rate, but the audio buffer is more important to pay attention to during scheduling, because if you schedule stuff off on the audio, you'll hear little clicks or beeps in the music, which I don't know if some of you who played older games, if you could sometimes hear if the audio gets a little bit off, you'll hear little static sections every once in a while. That's due to the improper scheduling. The scheduler is a host CPU thread that helps to solve these scheduling hardships. So during each video retrace, the scheduler reads the tasks generated by each client thread, and adds them to either the end of the real time for audio or the non-real time for graphics, because the graphics are running slower than the audio. For the development system, which is basically, so this is what you would buy if you were wanting to be a developer on a Nintendo 64 system. The ROM on the game cartridge is replaced by a RAM of the development board, which I show below here. This allows game developers to load the program to memory, control its execution, and observe the effects of modifying the game without having to rebuild every single time. So many of the devices needed for this are provided with the development board of the Nintendo 64. So what's included here is like the audio plugins, the video plugins, all that stuff. So there are some restrictions, which we kind of mentioned earlier, but good to talk about them again. So developers must use the Nintendo 64 OS. You can't like work on a PlayStation OS when working with this thing, or else that won't work, obviously. Developers should note, as Matt talked about earlier, there are priority threads which come with the rendering of the game, and the Nintendo 64 OS has priority threads 0 through 127. And if you ever schedule anything with a priority thread higher than 127, the game will crash because it doesn't recognize it. However, it is good to know that there should always be an idle thread assigned to priority 0. Basically, idle processes are running in the background, like Mario games, like keeping track of your coins, stuff like that. There must be a call to a main thread. Of course, in any code, you have to have a call to a main, or else the program won't run. Once the above criteria has been met, you can program on here to your heart's content. So the biggest part of performance tuning on Nintendo 64 is to discard as much geometry as possible before animation computing and rendering. Matt talked about that a little bit with the video side. So the standard GSP Fast 3D does all the stuff that we're used to: graphics, lighting, clipping, texture coordinates. As mentioned earlier, it stores these in a vertex cache. In order to process data from this cache at a faster rate, it is recommended the developers write code that pulls large blocks off this vertex cache instead of just like pulling one off at a time. It should be noted also that when developing these games, it will always help with proper performance if the developer sticks using textures for complex group of geometries. So don't like render like 5,000 triangles near each other, but instead use a texture for that type of stuff. GSP Turbo 3D was an older system that was replaced by a GSP Fast, but it is used to increase speed if it's just rendering the main character in the middle of the screen, the stuff that like never is really going to change. Full speed rendering on this system can only be done if a developer properly utilizes all these pieces of machinery we've talked about. Without parallelism between the CPU and RCP, hitting max speeds of the 30 frames per second just isn't an option. So we mentioned microcode a lot, but it's good to talk about what it actually is. So RSP boot enforces synchronization between, and this is one of the video microcodes, it forces synchronization between the CPU and RSP, which provides that parallelism that helps him boost the performance speed. There are 5 very basic versions of the graphics microcode. As mentioned in the last slide, GSP Fast 3D and GSP Turbo 3D are the 2 most commonly used. All types of RSD microcode generate commands for the RDP, which we talked about earlier, where the RSP was sending the commands to the RDP. For audio microcode, the N-Audio library is the main thing that we use. The N-Audio library is an improvement of an old library, which is the SGI, or the SGL audio library. The N-Audio library also provides a significant improvement on the audio processing when compared to the SGI. In this audio library, there are 2 unique types of players which have their own sets of microcode. One is a sequence player, which Matt talked about, and one is the MIDI one that only like plays the little cuts of bit music. SI devices, those are the devices that you like plug into your Nintendo 64. You know, the controllers we know about, or the ones we mainly use. I don't know if any of you guys had Nintendo 64 as a kid. The ones that you like, you have your controller, you have the memory pack, the rumble packs, basic stuff like that. There's also like, they also had a mouse for it, which you use in some games. Also like a Game Boy Advance plugin, and also a voice recognition device. So these basically work like any regular device we talked about during this class. They have the 3 commands: device initialization, executing actions on here, and returning the device status. So the EPI system, this was the memory card on the game card itself, or the system itself also had a small memory card, just not as big as the memory packs you could plug into the controllers. So it runs off an runs off of a EPI system, which is different than the OSPI functions. The old functions allow the programmer to access the memory space of the memory card ROM, but then they came out with additional stuff with like disk drives that you plug in the Nintendo 64, so it couldn't access those. So they changed to OSEPI, which allowed you to find, as a developer, those external disk drives. Currently, the available size for storage on the system was just 256 kilobytes, so yeah, very small memory there. I think that was our last slide.
Okay.
Yep. Cool. Thank you guys for all listening for a while. There's a lot of information we had to cover here because there's a lot of stuff to do with that system. So
Any
thank you all.
questions?
Cool. All right. I'll end this.